bit after 11, so we're going to go ahead and get started. Welcome to your third week in the course. Can everybody hear me okay?
Yes.
All right, I'll take that as a yes. Glad to see you all. This is lecture 7, by the way. So today we are going to go over a couple of different types of addition reactions with alkenes. And if you didn't remember, an alkene is just a carbon-carbon double bond, which looks like this. We're going to talk about Syn addition and anti-addition, as well as what's called Markovnikov additions and anti-Markovnikov additions. And also, just a brief housekeeping note, I made sure to edit the tutoring poll on Canvas so that people can submit more than once. So if you're somebody who would like to get some help looking over your exam or your homework after grades come out, feel free to try and submit the poll again. And if it doesn't work, just let us know. All right, so the general pattern that we're going to see a lot for these alkene addition reactions is that the double bond acts as a nucleophile by attacking an atom on another molecule. Usually it forms an intermediate, which is frequently a carbocation, but as we'll see, it can be another type of intermediate as well. And after we create this intermediate, the intermediate is attacked at an electrophilic point, creating the product. And when I say an electrophilic point, I mean some point like a carbocation or maybe a carbon or an atom that might not have a complete octet. Two different types of addition that you're going to need to learn about include Syn addition and anti-addition. In Syn addition, we have atoms that add to the same face of the molecule. So I'm sure that you're used to seeing alkenes like this, and here this alkene is written so that we're looking at it straight on. You know, like pretend the alkene is like my hand and you're looking at it just like this. So that's why we have these two methyl groups on wedges, and we've got the ethyl and the hydrogen in the back. So for Syn addition, the two atoms are going to add to the same face of the molecule. So let's say I'm adding 2 hydrogens. I'm going to draw arrows to show that they're both going to land on the same face of the hydrogen, or of the alkene, rather. Is the screen sharing back on?
Yes.
Okay, thank you so much. Sorry about that. Anyhow, in anti-addition, as you might imagine, the atoms are going to add to different faces of the double bond. And when I say different faces, I mean one might add from the top and one might add from the bottom. So in this case, I'll draw maybe a bromine coming to join from the top, and then another bromine coming to join from the bottom. And that's how anti-addition works. And we'll talk more about those as we discuss the following different types of reactions. So before we got into any hardcore mechanisms, I wanted to briefly review some carbocation stability like we talked about on Friday. So if you remember correctly, a tertiary carbocation, which is right here, is the most stable form of carbocation. And the least stable form of carbocation is the methyl carbocation. And I bring this up because stability is very, very important in organic chemistry. More stable intermediates, like a tertiary carbocation intermediate, is easier to form and preferred. So it's something you need to keep in mind when you look at doing these reactions. So next, let's go on and talk about our first form of reaction for Syn addition. I'm going to be doing a reaction where we have an alkene with H2 gas and palladium over carbon. And palladium over carbon is just a catalyst. So it's not super involved in the actual product of the reaction. You'll learn a little bit more about what it does in 3570 this fall, but for now, don't worry too much about it. I'm going to go ahead and draw my alkene. I'm going to draw my hydrogen gas and my palladium over carbon, or not. There's my palladium over carbon. And I'm going to get the following product. There we go. So as you can see, the hydrogens, which are in blue here, added to the molecule on the same face, just as I showed when I defined Syn addition a little while ago. It's important to know that in Syn addition, both of the added substituents need to be on the same face of the molecule. So they must both be straight lines or wedges or dashes. So I'll give you, to illustrate this, another way I could draw the product for this reaction. Suppose I had drawn things sort of like this, where instead of the two blue hydrogens being on these straight lines, I'll put the methyl groups that are in the front of the molecule, the one that's in the front of the molecule. And this is not actually a methyl, I'm sorry. This is supposed to be a hydrogen. I'll put those on the straight lines. And I will put these this methyl and this hydrogen, those are on the dashes. And then suppose I put the hydrogen that added from the reaction, I can put those on the wedges. These two products are both considered stereochemically the same because they both show that there was Syn addition going on because both of the blue hydrogens are on the same face of the molecule. And that's super important when drawing your products. So now we're going to go ahead and discuss another form of Syn addition where we have another alkene reacting with H3O+. Now it's important to note that you might see this reaction shown where we have an alkene reacting with H+ and H2O, any source of H+. As I'm sure you remember from 2080, there's this equilibrium that constantly goes on where we have H3O+ dissolving into H+ and H2O. So either of these two forms, either an alkene with H3O+ or an alkene with some H+ ions and H2O, you might see this H+ in the form of HCl or H2SO4 or any strong acid. Either of those is acceptable and they both mean the same type of reaction is occurring. So I'll draw a quick overview of the reaction before I get into the mechanism. Basically, we're just going to have, and it looks like screen sharing turned off. Basically, we're going to have an alkene reacting with the H3O+, and creating this nice new molecule. Where we have both an alcohol group and a hydrogen, which are both added on the same face of the molecule. And I didn't draw the product in 3D for the overview, but I will for the mechanism. So I'm just going to go ahead and move this overview up to the side. And let's go ahead and draw the mechanism for the reaction. So as is the case for most alkene reactions that we're going to discuss, our double bond is going to go ahead and attack a hydrogen on the other molecule. In this case, the other molecule is the H3O+. And the electrons in this oxygen to hydrogen bond, they're going to go on to this oxygen. And since the oxygen H3O plus has a plus charge, that means it's electron deficient. So it's more than happy to gain some more electrons. Now, when this occurs, we create a carbocation intermediate. I'll go ahead and draw in all the hydrogens this time to make things really clear. So this is our intermediate right here. Can anyone tell me what type of intermediate we're looking at? It's a carbocation intermediate, but which type?
Secondary?
Yes, exactly. This carbon right here, which has the plus charge on it, it's attached to one CH3 group up here, and then this other carbon over here. So it's got two carbons on it, and it's a secondary carbocation intermediate. Great job. So our carbocation is going to be attacked by an incoming water molecule, which we created earlier. And it's going to go ahead and create another, not quite another intermediate, but we're still not at our product yet. We've got our one hydrogen from before, but instead of having our alcohol group yet, we've got an oxygen that's bound to two hydrogens and has a plus charge. So we're still not quite where we want to be. What happens is this oxygen gets deprotonated by another water molecule, because as we discussed earlier, we have this reaction up top going on continuously, where the H2O plus goes and disassociates rather into H plus ions and water molecules. So I'm going to draw another H2O coming to deprotonate a hydrogen off our molecule, and that gives us our product. So we have our hydrogen from before, and we have our alcohol. And I'm going to take this opportunity to say that we will expect you all to know both the overview, so like be able to give the product for this reaction if we give you the starting material and the reactant. And you're also expected to know how to draw out the mechanism for the reaction. Some reactions, like the previous example of Syn Addition with the H2PD over C, that one didn't necessarily have a mechanism, but most reactions do. So it's important to take notes about that. There we go. Are there any questions so far? Alrighty then, I'll go ahead. So now that we've gone and talked about a couple examples of Syn Addition, I'm going to go ahead and talk about anti-addition. For a big example with anti-addition is having an alkene react with Br2 or Cl2. Both of these reactions occur in the exact same way. So I'll go ahead and draw the overview of the reaction so you know what to expect when I draw the mechanism. I'll draw an alkene. And then this reacts with our Br2 to make this product. And then because it's anti-addition, both of our bromines are going to be on opposite phases of the molecule. So one bromine is going to be pointed down like this, and the other bromine is going to be pointed up like this. So let's go ahead and draw out the mechanism so we can see how these things occur. So once again, I'm going to go ahead and draw out our alkene. And as you might imagine, the double bond, once again, is going to attack an atom in the other molecule, which is the Br2. So I'm going to draw an arrow from the double bond to the bromine, and the electrons in this bromine-bromine single bond are going to go on to our other bromine. So we're going to create Br-. And in this reaction, we're going to get a different type of intermediate. We're going to have our 2 methyls, which are over here. We're going to have our 1 methyl, which is on this carbon. We're going to have our hydrogen, which I didn't show in the original starting material, but there is a hydrogen here. I'm going to draw that in, because why not? But then we're going to have our bromine. And if you might remember from the other sorts of alkene addition problems that we've done, normally the bromine joins one of the hydrogens. I'm sorry, normally the bromine joins one of the carbons and creates a single bond to that one carbon. In this example, however, the bromine actually is going to have bonds to both of the carbons in the molecule. And it's going to have a positive charge. This intermediate, which can be called a triangle intermediate, is also known as a bromonium ion. Sorry if that's a little hard to read. And in anti-addition problems, the triangular intermediate is attacked by the Br- that we have floating around in solution. The Br- is going to attack the more stable carbon. And remember, we can determine carbocation, well, not carbocation, but carbon stability in a similar way that we evaluate carbocation stability by the number of carbons that each carbon is attached to. So based on that, which carbon is our Br- going to attack? It's either going to be this carbon or this one. Would anyone like to take a stab at that?
The one on the left?
Exactly. Great job, Nestor. Thanks for answering. The not carbocation, but the carbon on the left side of the molecule is more stable because it has 1, 2, 3 carbons attached to it, while the carbon on the right only has 1, 2 carbons attached to it. So I'm going to go ahead and draw my arrow from the Br-, which was created in this step of the problem, going to attack this carbon. And this attack is what's known as the backside attack, because if I were to draw this molecule out, you guys would see the bromine like attacking from the back or like the other side of the molecule. So after our carbon right here is backside attacked by the bromine, the carbon-bromine bond breaks because we couldn't have a carbon with 5 bonds. And the electrons in this bond go on to our bromine, which is more than happy to take them because bromine is a pretty electronegative atom and it's not too happy with a positive charge. So I'll go ahead and draw our product. So again, we have 1 bromine pointing up, this is the one which was already in the molecule in the triangle intermediate. And then we have the Br at the bottom, and that's the one that came in and did the backside attack. So this is how we end up with a product where we've got one bromine on the top and one bromine that's on the bottom. Are there any questions so far?
I have a question. Since you said that this is done with Br2 and Cl2, why can we assume that since they are both they're both comprised of halogens, that the other halogens can do something similar?
That's a great question. The only two reactions which I've ever seen, the only two halogens which I've ever seen do this reaction are Br2 and Cl2. So the other TAs can correct me if I'm wrong, but I'm pretty sure it's just bromine and chloride that can do this reaction. Just those two halogens.
Okay.
I agree.
Okay. That's a great question, though. Thanks for asking. So I'm going to go ahead and draw out another type of anti-addition problem. And this reaction actually goes almost exactly the same as the reaction we just learned. So I'll go ahead and I'll draw out the same alkene as before, only in this case, we have a water molecule in addition to the bromine. So I'll draw out my Br2 up top and my water molecule down below. And our product, I'm not drawing 3D structure this time, in the interest of time. Is going to look something like this, where we do have our one bromine, but instead of having another bromine at the bottom down here, I'm going to draw in an alcohol group. So as you might be able to guess, this molecule was created by the same method, but the water molecule does the backside attack instead of the bromine. So let's go ahead and draw the mechanism, so we can see how this occurs. So I'll go ahead and draw my arrow from the double bond attacking the Br2. That creates the Br minus. And then we create our triangular intermediate, or our bromonium ion. And again, since this is the exact same alkene, our left carbon is going to get attacked, not by a bromine, but by a water molecule. So I'll go ahead and draw that in. And then we have to go ahead and break this bond between the carbon and the bromine, because we've got a new bond forming between carbon and oxygen, and carbon can't have 5 bonds, so we've got to break this bond in our triangular intermediate. So we get a product that looks sort of like this. Well, not quite our product yet. I'll hold that thought. We've got our oxygen and we've got 2 hydrogens. And does anyone remember what we did when we had a water molecule attacking a carbon the last time to get rid of that extra hydrogen?
You added another H2O molecule.
Exactly. Thank you for sharing. So basically, anytime we have a water molecule forming one of these alcohols, we're going to need to deprotonate the incoming water molecule, because what we end up with if a water molecule attacks is this O with a positive charge and 2 oxygens, and that's not quite what we want. So I'm going to draw in this additional water molecule, deprotonating the other water molecule. And this is how we end up with our actual product. And now we have our bromine up top for anti-addition and our alcohol group down below. So as you can see, this reaction is very, very similar to the one we just did with the two bromines. The only difference is that the water molecule in solution attacks the carbon before the Br- does. So that's the only difference. Any questions before I go on? Okay. So I want to talk a little bit about stereochemistry with anti-addition because it's definitely very relevant, and a lot of problems that you can expect to see on the homework and our exams and Dr. Gannam's exams in the fall is where you are required to draw out the stereochem for a certain reaction. And that actually can be worth almost as much points as recognizing the correct reaction itself. So there's one thing I can impress to you, is that stereochemistry is incredibly key when talking about these reactions. So if I were to have a Z alkene reacting in this problem, I would end up with a product and its enantiomer in an anti-addition reaction. So let me give an example. Let's say I had a molecule that looks like this. I've got both my highest priority groups on the Zane side. That's how I'd like to remember it. And so it is a Z alkene. If I had that reacting with, let's say, Cl2, I would end up with the following product. I would end up with this molecule right here. Oops, that's not a hydrogen. That's a chlorine and another chlorine. However, this wouldn't be the only product that I would end up with. I would also get the enantiomer of this molecule on the left, which I'll go ahead and draw. A lot of times, if you end up with a product and you know that an enantiomer of the product is going to form, it's all right to just write plus enantiomer next to one of the products. But I'll go ahead and draw them both for demonstration's sake. So these two products are both enantiomers. I'll go ahead and draw up the stereochemistry configurations for each of these carbons in the interest of time. These two carbons are both S, and these two stereocenters are both R. So if you didn't notice that these molecules are non-superimposable mirror images of each other, you could have looked at the stereochemistry conformations and seen that they were perfect opposites. So that can be another indication.
Well, the thing is, Bob has a gift card to the first place. So we were thinking.
So that's for our Z stereoisomer. Now another example is if we have an E stereoisomer. So I'm going to go ahead and draw our highest priority groups. We've got our two highest priority groups on the opposite sides. So this alkene is E, not Z. And I'll draw the same reaction. I'll draw it reacting with the Cl2. And this is our product that we get. It ends up being miso. So again, we have one chlorine facing up and one chlorine facing down. Can anyone remember what a characteristic of meso compounds is? That would be willing to share?
Plane of symmetry.
Exactly. Thank you for sharing, Emma. So meso compounds have a plane of symmetry. And does anyone know where the plane of symmetry is in this molecule?
Right down the middle carbon.
Exactly. So I'll go ahead and draw that quickly in the interest of time. But this molecule has a plane of symmetry, so it is meso and achiral, since we have the two stereocenters in the plane of symmetry. So that's just something to keep in mind if you ever see an E stereoisomer in this reaction, and they ask you to write the products. So quickly, I want to do another example of anti-addition if you have a ring, because this was something I found incredibly confusing when I studied 3570 this fall. So I'll go ahead and draw my ring. And I'll put on the CH3 and I'll add a deuterium. And let's do another anti-addition problem. I'll do the one with the Br2 and the water molecule. And as you probably remember, if we do this reaction, we're going to end up with a triangle intermediate. So I'll go ahead and just decide that maybe the methyl group is on a dash, and both carbons are connected to the bromine using wedges. And I'll say that the deuterium is connected using a dash as well. Well, our water molecule, if you remember, is going to go in and attack the carbon that is more stable, which is this top carbon up here, since it's connected to 1, 2, 3 carbons. So I'll draw my arrow, and I'll draw my arrow of the bond breaking between the carbon and bromine up here. And then something interesting occurs when I draw the product. Our CH3 from before is now going to be on a wedge. I'll draw the alcohol. In the interest of time, I won't show the deprotonization. The bromine is on a wedge, and the deuterium is on a dash. And you might be wondering, Sydney, what's the big deal? We've seen this reaction like several times already today. Well, before, the methyl group was on a dash, and here it switched to being on a wedge. This is because whenever you have a backside attack, you always have what's known as inversion of configuration going on, which we'll talk about a little bit later in the course. Here, inversion is shown by having the groups that are on the carbon that's being backside attacked, they change configuration. We have the CH3 that's on a dash switching to become a CH3 that's on a wedge. And this is because we're using a ring structure. In our alkenes, we're able to show inversion by having one bromine facing completely down opposite in direction from the other bromine. So we can have stuff that looks like this. However, in a ring structure, we're forced to use our wedges and dashes for the bromines. So to show that inversion of configuration here, we have the CH3 change from being on a dash to a wedge, or vice versa. And of course, the carbon that was not backside attacked remained completely unaffected. Are there any questions? If not, I will go ahead and pass the rein to Samantha.
Thank you. Let me, wait, what am I doing? Share. Is it gonna share? Let's see. Okay, can everyone see this? If nobody says anything, I'm gonna assume you can see it.
See Sam, or at least I can.
Thank
Me
you.
too.
Out of the way. Sorry, give me 1 second. Zoom is being a little bit whack. Okay, so now we're going to be talking about Markovnikov's rule, and this is something that you're going to see a lot, especially in 3570. Make sure you're listening. So as we've been talking about, this is going to be alkene addition again, so just 2 C's double bonded with stuff around them. And the important thing to remember about Markovnikov's rule is that the product with the most stable carbocation intermediate is the preferred product, or in other words, the major product. Sometimes you'll get minor products where you have the less stable carbocation intermediate, and yeah, like I said, this is going to be the minor products. I'll show you some examples. So for most of these, for a lot of these, we're going to be using this reagent called, hydrogen halide, like Sydney mentioned. The X just stands for basically any halogen. The most common ones you're probably going to see are Cl, Br. Once in a while I'll see iodine, so I'm just going to put that there. And so the X is going to add to the more substituted C. And if you remember, that just means the C with the most other carbon attachments. And on the other hand, and I think this is a little bit easier to remember, is that your H from your HX is going to go to the carbon that already has more H's. And if this seems a little bit confusing, I'm going to go ahead and give you an example. So down here we have an alkene and HX. And so let's go ahead. Double bond is going to hit the H. Going to take off the X. Let's take that off. And so I'm going to go ahead and draw it like that. And the reason I'm doing that is because I want to show you this. So this hydrogen here, this carbon on the left already has 1 hydrogen. The carbon on the right does not have any hydrogens. It's just attached to these R groups. And so your H from this HX is going to go, like we said, to the carbon that already has the most H's, which in this case is the guy on the left. So your H from the HX will go on the left, so he's with his buddy. And so this is a carbocation, because we only have 2 attachments right now. Remember, you got your halogen ion just floating around. And so can anyone tell me real quick, just shout it out, what kind of carbocation this is? Is it primary, secondary, tertiary? What do you guys think?
Tertiary. It's
Yeah.
the one with the arrow, right? Pointing.
Yeah, sorry, can you say that again?
Tertiary.
Yeah. Thank you, Nestor. Yeah, it's tertiary. That's perfect. So your X is just gonna hit it. And it will give you a structure that looks something like that. And so if we want to double check that this follows Markovnikov's, you can go, okay, where did the X go? It went to the carbon that already has the most other carbon attachments. Remember then our group is usually going to be some carbon with maybe attached functional groups. And your H, which I think is the easier thing to remember, the H is going to go where the other H's already are. So H goes with H for Markovnikov. Anyone have any questions about that? Okay, so now we're going to be talking about anti-Markovnikov. And so this is basically exactly what you think. It's just literally the opposite of Markovnikov. So before we said that H attached where there are already H's. Now H is going to go where there are less H's. So another way to remember it would be that the X from the HX is added to where there are already H's. And so a lot of the times you'll see this when you use HBr in something like a peroxide. So anything that has like free radicals. And you don't really need to be worried about this for now, but free radical, if you remember from Gen Chem, normally you have like, let's say you have an oxygen and you have a bunch of lone pairs. I'm just gonna give them an R group for fun. So free radical will be when instead of your lone pair, you have a single electron just floating around by himself with nobody. And let's go ahead and use HBr because that's what's up there. One way you'll see peroxides added is through ROOR. So R is just going to be some kind of R group. You can also maybe just write peroxides. Sometimes you'll see something like HOOR, I believe. There are a couple others. You don't need to be super worried about them for now. And then a lot of the times you'll add heat or light. Let's make this red for fun. And so I'm not going to show you the mechanism because it's not super important for now, but we want to go ahead and draw what happens. It's going to be your first product. There's going to be a bunch. And draw. Did I miss anything? That'll be good. And so we can look again and decide that this isn't Markovnikov, this is anti-Markovnikov, because this carbon on the top of this alkene is the one with the H. This guy in the bottom does not have any H's, he just has two attached groups. And so the H from the HBr is actually going to add to the bottom, so where you expect it wouldn't go, because again, this is anti-Markovnikov, not Markovnikov, and Br, the halogen, is going to go to attach to the carbon that already has H's. And so you'll see here, yeah, same thing happens on the bottom. And you're actually also going to have two enantiomers. I didn't want to draw them out, so there they are. I'll give you a minute if you want to write those down. But something that you might also I'll just show you this real quick. See your professors use is, let's say you had some starting product A and you use B on it, whatever B is, and then you get C. If C's enantiomer is also created, they might just write like C plus enantiomer. So in this case, instead of drawing this guy out, you could just put like plus enantiomer. On exams, I would draw out the enantiomer if they ask for it. A lot of the times they'll tell you whether or not they want it. So don't be super worried about that. And so We can look at these guys again. So I'm going to look at the top two real quick, and we'll see that they are both anti-addition, because if you remember, this Br is new, this H is new, this Br is new, this H is new, and one is on a wedge, one is on a dash, one is on a dash, one is on a wedge. So they're adding to the opposite sides. This is anti-addition. We can go down to the bottom, look at Br, look at the H again. This time we're going to see they're either both wedges or both dashes. So these are Syn. So just a little throwback to Sydney's part. Does anyone need another minute to copy these down? Are you guys good? Okay, I'm going to assume you're good.
I have a question.
Yeah, go ahead.
Like, why did you draw two pictures on the top and bottom?
Yeah, so the enantiomer, in this case for this reaction, you're always going to create the enantiomer. So if I were to turn this guy around, oh, can you see my red?
Oh, yeah. Yeah. I could see.
Yeah, if you were to turn this guy around, he would be the mirror image of his friend on the left. Does that make sense?
Yeah, I was just confused, like, why you have, like, I get why you wrote the enantiomer.
Oh, like these two guys? Yeah, so
Yeah,
in this case, the anti and the Syn product both form.
Oh,
It'll
okay.
make more sense when you actually learn, what do you call it, like free radical and other Anti-Markovnikov additions in the actual course, but free radicals are kind of scary to talk about because those are a very long synthesis, so we're not going to talk about them for now. Does that sort of help?
Yeah, that helps. Thank you.
Right. That's a good question. And so, let's see, yeah, we will also be covering more Anti-Markovnikov additions later this week, so if it's a little bit confusing, don't worry, you have a ton of time. I'm going to do a little quick check. I'm going to say, what are the products of this reaction? So again, alkene with an HX. In this case, the X is just going to be the chlorine. And so I'm going to go ahead and draw. I don't want to do this. I'll just go ahead. It's going to be one product. And this will be your other product. And so can someone tell me which one is the one on the left, Markovnikov or Anti-Markovnikov addition?
Markovnikov.
Yes, exactly. Thank you. So this is going to be your Markovnikov. And this is going to be your major product. And if anyone's confused, again, the carbon on the right, in this case, has the H. So we're going to add our H to be with his buddy. So this guy has to be Anti-Markovnikov. He's going to be minor product. Anyone have any questions on that? All right. There are a couple things you want to keep in mind when you're doing these problems. One of them is going to be hydride shifts. And so hydride, again, is just going to be like an H group on something. Let's just do HR. That looks kind of whack, but oh well. So a hydride shift, for the most part, usually occurs if you have a tertiary carbocation next to a secondary. It can also occur from like tertiary to primary, that kind of thing. I'm just going to write this out again. A lot of the times you will see professors abbreviate tertiary or primary or secondary carbocation as this like kind of weird 3 or 2 or whatever number with a degree sign. So just be aware of that. And if we go back, let me just write secondary real quick. So like C+. If we remember, tertiary carbocations are going to be more stable than secondary, which is more stable than primary. And so I'll show you an example of a hydride shift. Can anyone tell me what kind of carbocation that one in blue is?
Tertiary?
Really close. This is actually going to be secondary because he's attached to one carbon group on this side, one carbon group on this side, and this guy on the right would actually be tertiary. Imagine looking at that one. If he were a carbocation, in this case, he is not. Doesn't have that plus charge. And so, if we remember, tertiary is going to be more stable than secondary. So what we want to do is to change this carbon in red on the left into a carbocation, but make his friend no longer a carbocation. And how we do this is we literally just shove the H over onto the other carbon. This only works between carbons that are right next to each other. Oops. And so now you see that this guy on the left no longer has that extra hydrogen pointing wherever. And now the carbon on the right has taken this hydrogen and just shoved it on here. So now this is no longer a secondary carbocation, but this guy is now tertiary. And like I said, this is preferable because tertiary is more stable than secondary. And so if I want to show you an example where it's not a carbocation at first, sometimes you'll see it where you'll have a leaving group first. So in this case, the halogen, bromine, will just become an ion. Let's just say this is the water. This is now carbocation, bromine's just out here vibing. We have the same issue where the carbon on the left would be a tertiary carbocation. The carbon on the right is secondary. That is not preferable. So we're just going to shove his friend over. This is still happening in water. I'm going to draw the lone pairs for fun. So now hydrogen is now over here. This guy is now a carbocation. You have your BR here still just doing its own thing, but you can ignore it for now. And lone pairs are going to come and attack. I'm going to draw like that. So you will get something alike. It's going to be ugly. Did I miss anything? No. And then that will get deprotonated as usual. I'm just going to have him read H2O. It's going to come and steal hydrogen. Get rid of that plus charge. So you just have some H real plus. Just having a good time over there. And then 1, 2, 3. then your end product will look something like that. Anyone have any questions on that? Okay, so second thing to watch out for is going to be methyl shifts. Sometimes, I think online, I've seen them called alkyl shifts. So if you Google and see that word, you know what it means. A lot of the times your professors, at least when I had GANM and fours, I think they almost always called them methyl shifts. One of the TAs can correct me if I'm wrong. And so this is going to occur when you have a quaternary carbon next to a secondary or primary or that kind of thing. But the important thing to remember here is quaternary. So these aren't going to occur as readily as H shifts, just because these methyl groups are relatively big compared to hydrogens. You know, like hydrogen atoms are just these like little tiny things that can zip around. But methyl groups, not so much. Those are kind of bulky. And so I'm going to show you a quick example. And so let's say we start out with a carbocation. Notice here that there are no hydrogens on this guy. So there's this in green, this in blue. Oops. This guy in blue is going to be secondary carbocation because there's one carbon attached group, two carbon attached groups. And then this guy in green is actually going to be quaternary. He is not a carbocation, but he has 4 attached groups. 1, 2, 3, 4. And so essentially this is going to occur for the same reason as a hydride shift. The way I kind of like to think about it is if you saw this molecule over here on the left, you might be like, okay, well, that guy doesn't look good. Maybe we can do a hydride shift on him. But unfortunately, the guy next to him has no hydrides to give. So instead, he's going to give the entire methyl group. So let's see. You can see, let's do this. You can see this entire methyl group just moved one over, and now the carbon on the left is a carbocation, and he is going to be tertiary. This guy is also going to be tertiary. He's not a carbocation, but you can see that the carbon on the right is now a lot more stable, and the carbon on the left, like, he's fine. And so I'll show you another example, just using a structure that's really close to the one we just did. And so here again is an example. Oh, remember this little hydrogen over here. So this is not, at the moment, a carbocation. So your leaving group is going to pop off. Let's move them down a little. It's going to give you, I'll just draw the hydrogen. It's going to give you this. Again, you're going to have the same issue where the carbon on the right in blue is secondary. The guy on the left is quaternary. So he's going to give his friend the methyl group. Let's have this happen in water again. I forgot. Cl is just floating out there, H2O. And again, lone pairs on O are going to attack. For the purposes on time, I'm not going to show deprotonation. Just know that deprotonation happens here. It just happens almost exactly how it happened in the last slide. You have the H3O plus, H2O plus group connected to where the carbocation was. You get rid of one of the H's, and this results. Anyone have any questions? Okay, so the last thing we're going to go over real quick is regiochemistry versus stereochemistry. So as you can probably imagine, stereochemistry deals with stereoisomers. And so when we use words like syn and anti, that's describing stereochemistry. So an example, this is going to be a totally hypothetical alkene reaction. You'll see in a minute what I mean. Let's just do AB. As you can tell, that's not a real thing. But let's say some of the products looked like this. You don't need to be worried about how I got these products because, again, this is a totally fake reaction. Let's say there's some others. And so this on the left, you'll see both the groups that were added are pointing up, and on the, and then on the right, the A is pointing up, the B is pointing down. So this guy on the left, is this gonna be syn or anti? Does someone want to shout it out?
Syn.
Perfect, thank you. I think that was Gigi. Syn, and the other guy's gonna be anti. And so these are gonna be stereoisomers. And so on the other hand, regiochemistry is going to deal with constitutional isomers. So when we use the words Markovnikov and Anti-Markovnikov, that's going to be describing regiochemistry. And so I'm just going to go ahead, take what we just used, and I'm going to copy the first product. And then I'm just going to make up a second product. Let's do this. And they have some friends, but we don't care about them. And so in this case, we're going to see that A is on the left, B is on the right. But on the other product, B is on the left, A is on the right. So these are not stereoisomers. They're actually regioisomers, or you can call them constitutional isomers. In this case, Markovnikov and Anti-Markovnikov don't really apply because, again, this is A and B, there's no H. But just know that when we talk about Markovnikov and Anti-Markovnikov, that has to do with regiochemistry. Anyone have any questions on that? The last slide is just some advice Sydney has. Sydney, did you want to talk about that or? Sydney? Okay, well, I'm just gonna talk. So this is her advice. I think it's really good advice though. But like we've been saying, for everything in organic chemistry, just concentrate on stability. So when we talk about doing H or methyl shifts or following Markovnikov's rule, that's literally only because it creates a more stable product. Does that make sense to everyone? And we'll have a lot more examples for you. So if you have any questions, don't worry, you'll have a lot of practice. And that is the end. Does anyone have any questions before we finish up? There will be office hours. Oh no, I have to convert to EST. 5 to 7? Yeah, I can do math. There will be office hours 5 to 7 as usual today. So yeah, that is it. Everyone have a nice day.
Hi, actually.